Where does quantum mechanics stop? Classical physics describes our ordinary world, in quantum mechanics the world of tiny particles. So where do we draw the line? Hi, I'm a physicist, and the short answer to this is there is no strict line, because quantum mechanics does not stop. We believe we can use quantum mechanics to describe the whole universe. Okay, but then why don't we see quantum stuff happening in daily life? I mean, quantum mechanics says the cat is dead and alive before we look at it. But this is not really happening for cats, right? Well, actually it kinda is. But we're missing a step in between. Something that reveals why quantum mechanics seems to stop. I'll go over how we unravel all this in a second, but now let's jump right into it. Quantum mechanics leads to weird things. Particles are in two places at once, atoms have discrete energies, and cats are dead and alive at the same time. Well, except that cats are not dead and alive at the same time. At least I've never seen one. That is actually the reason why Schrödinger came up with this cat thing in the first place. He wanted to show that you can't just take quantum rules made for tiny things and apply them to big things. He said that the blurriness or fuzziness that arises in the quantum world becomes simply incorrect when we're talking about big things. And he didn't want to naively accept a blurred model as a valid representation of reality. What did he mean by blurriness? And doesn't that mean quantum mechanics indeed stops? Well, spoiler alert, we actually know something that Schrödinger did not know. In a sense, science is about challenging knowledge and challenging authorities. So let's challenge Schrödinger, who didn't want to apply quantum rules to big things, and see what happens if we do exactly that. So, in this video, we'll understand why we don't see dead and alive cats or planets being quantized like atoms, even though quantum mechanics does not stop. This is the third video in a mini-series where I try to answer our biggest questions about this super confusing topic. So, if you have any, please drop them in the comments below. Thanks! And of course you can watch this video on its own. We'll look at two unique effects of quantum mechanics, the quantizedness and the blurriness. And each time we'll see what happens to those effects when we go to bigger stuff. In the end, we'll know the thing Schrödinger did not know, the missing step. So, this is the effect of quantum mechanics which basically gave it its name, the energy levels of atoms. I explained those in my last video, but in short, electrons don't circle atoms, but they fill these so-called orbitals or shells. And each orbital belongs to a certain fixed amount of total energy. So the atom can only have these certain amounts of energy, these energy levels. The energy cannot continuously change, but it jumps between those discrete levels. This discreteness is kinda why physicists came up with the word quantum, and why we say the energy is quantized. So, electrons don't circle atoms, but the current energy level influences the electron's locations. Locations in the sense that the electron is actually in multiple locations at once. Think of a fuzzy electron cloud. That, being in multiple locations at once, is an example for the blurriness Schrödinger was talking about. And we will come back to it. But the important thing right now is that this not only applies to atoms, it applies to any bound system. Another example for a bound system is molecules. The atoms within them are bound by electromagnetic forces. So here, as you pointed out, quantum probability does not stop mattering. You also get fuzzy clouds and discrete energy levels. And now it gets really interesting, because molecules are just one example for bound systems, one that is still relatively small. But there are bigger examples for bound systems, way bigger, like planets orbiting the sun, bound by gravity. So, you can use quantum mechanics to calculate what happens here, and you'll find that the planets' orbits are also quantized, which means they have discrete energy levels. So, planets can in principle only be in certain orbits that belong to certain energies. And that's the thing that gave quantum mechanics its name. I mean, if that's not convincing to you that quantum mechanics does not stop. But yeah, actually, if you do the math with the big masses of planets, you'll see that the gaps between different allowed energies are way too small to measure them. So that's why it's perfectly valid to just use classical physics to describe planets. Okay, so planets' orbits are hypothetically quantized, but in a way that's not even close to being measurable. And a planet is not like a fuzzy electron cloud. We can see the planet's orbit. And the cats are still not dead and alive. So we're back to quantum mechanics stopping at some point? I mean, why is there nothing blurry about a planet's orbit? Why are there no dead and alive cats? To understand that, we first need to know why there should be dead and alive cats in the first place. So now we'll uncover what makes quantum mechanics so weird, to then see why its weirdness disappears. So, what makes quantum mechanics quantum mechanics? You probably know Schrödinger's cat. There's a poor cat trapped with radioactive atoms, which may or may not decay, but if they decay, the cat gets killed. It demonstrates what sets quantum states apart from a classical state. What's a state? Well, that's just how we call the description of the current situation. We look at a part of the world which we call a system, like a cat in a box. And whatever is in there right now, that's the current state of the system. In a classical world, the things you see are the only possible states of a system. You can see dead cats and living cats. So, the possible states are dead or alive cat. What does quantum mechanics tell us about possible states? It tells us that they are solutions to the Schrödinger equation. You can't understand the Schrödinger equation if I just show it to you like this. I would need to specify what everything means, especially this year. But we don't need to go into details. Importantly, this side of the equation asks how will the state change over time, and this side somehow has the answer. You can compare this to Newton's force equals mass times acceleration. Here, this side is asking how will the state change over time, and this side has the answer. Now, only solutions to this equation are valid states. States that actually belong to the system. And here's what sets quantum physics apart from classical physics. If you have two or more solutions to the Schrödinger equation, the combination of them must always be a solution as well. What does this mean? This means if you have two possible states like dead or alive cat, the mixture of those states must be possible as well. So the dead and alive cat is a valid state of the system. We call this combination or mixture of states a superposition. So the cat can be dead or alive and therefore also in a superposition of being dead and alive. Simply because that's what the math tells us. If this video tells you something interesting, please leave me a like. Thanks. We can use the superposition to calculate how likely it is that we will find a dead cat or a living cat as soon as we look. But the superposition is not just a classical sum of possibilities. Loosely speaking, the different things within a superposition can talk to each other. It's all blurry. Yeah, our language hasn't really caught up to the physics here. The best it allows us to say something like the cat is dead and alive at the same time, or quantum states are blurry. So, just note that the fact that this is a superposition and not just a classical sum of possibilities has some mathematical consequences for the theory. Together with the uncertainty principle, this superposition thing is mainly responsible for all the weird things happening in quantum mechanics. An electron in an atom can be here or here or here. So, it can also be in a superposition of all those places. That's the fuzzy electron cloud I mentioned earlier. It's a superposition of different locations. How do we know that such superpositions actually exist? I mean, again, I've never seen a dead and alive cat. Well, under the right circumstances, we can see what happens when the different things within a superposition talk to each other, when they interfere with each other. We see this communication if we look at interference patterns. That's something I will talk about next week. But for now, states can be in superpositions, and a superposition somehow communicates with itself, which has some consequences. That is what makes quantum mechanics quantum mechanics. But what makes it go away? Why does a quantum state lose its blurriness? There's something I didn't tell you about Schrödinger's equation. It only works for closed systems. A closed system is an isolated part of the world, so there's no interaction, communication or whatsoever with anything outside the system. But Schrödinger's cat? Even if you see the box, there's not just the cat, the box and the radioactive killing machine. There are, for example, air molecules that constantly bump into the cat, or there's radiation passing through the box. The cat is so big that there's a lot going on. Macroscopic systems are never isolated from their environments. Therefore, they should not be expected to follow Schrödinger's equation, which is applicable only to a closed system. Okay, so quantum mechanics does not work here, so it stops? We have to throw it out? No. Instead, we have to treat quantum mechanics seriously. Instead of treating the cat in the box as one closed quantum mechanical system, we have to put everything together: the cat in the box, the measurement apparatus, and the environment. If we take radiation or air molecules bumping into the cat into account, they become part of the superposition. Previously, we had the superposition cat is dead with cat is alive. But now, we have the superposition cat is dead and molecules bump into a dead cat with cat is alive and molecules bump into a living cat. And if you do the math, you will see that suddenly the two parts of the superposition cannot talk to each other anymore. The state lost its blurriness. Sometimes people say the environment measures the cat, but I'm not a fan of this. The measurement thing is weird. We're looking at something and suddenly it goes from a superposition of possible outcomes to one definite outcome. But here I'm not talking about a hard cut that comes out of nowhere. This is a smooth transition that comes out of math. When the environment enters the superposition, the talking of its parts, the consequences of the superposition, average to zero. So in principle, there is a short moment where the cat is indeed in a superposition of dead and alive, and where the parts of this superposition talk to each other. But when the environment enters the game, this talking averages to zero. We are only left with two possibilities: cat is dead and molecules bump into a dead cat, or cat is alive and molecules bump into a living cat. We call this process decoherence. We have not even looked at it yet. Up to now there was no measurement, but the possible options have already been reduced. That is the step in between, the step Schrödinger did not know about. That's why we can never see a dead and alive cat. This option is already gone before we look at it, just due to the interaction with the environment. Of course, decoherence happens not only to cats, but to everything which is big and warm, whereby big roughly means bigger than a molecule and warm means just more than a few degrees above absolute zero. Big things just have a lot to interact with and warm things radiate a lot. Side note, yes, you, me and everything sends out electromagnetic radiation. The warmer you are, the higher the energy of this radiation. So, big and warm things interact so heavily and frequently with the environment that the possible options are reduced extremely quickly. And the bigger or warmer something is, the faster this happens. So technically, decoherence is why we have fuzzy electron clouds, but no fuzzy planet clouds. On big scales, all the quantumness averages to zero. If you're wondering how this averaging to zero works or why it's called decoherence, I will talk about this in my next video next week. Thanks for watching. Have a wonderful day.